Okay, so 3.3 is where we actually start getting into quantum mechanics, because 3.2 and 3.1 sort of were just very much introductions or slash reviews of quantum mechanics or not quantum mechanics, linear algebra, and sort of a very basic introduction of how it can be applied in terms of quantum mechanics. So the big thing that we've sort of taken away from the early sections of chapter 3 is basically the eigenvalue expression, which is q hat operated on our eigenfunction f, giving an eigenvalue little q multiplied by that same eigenfunction f. So in this case, f is a vector that represents our wave function. Q hat is whatever operator we're trying to measure, and the eigenvalue little q is the actual value that our measurement takes. So, if q hat represents, say, the operator for velocity, then little q is going to give the actual value that velocity, it's going to give the actual velocity of our system when we measure the velocity. So applying an operator on an eigenfunction vector is basically analogous to actually doing a measurement for some value in our actual system in a physical sense. So in general, if we say that q is some number that represents a measurement, in this type of expression, there's two possibilities for the values that q can take. So possibility one is basically saying that q is discrete, aka discrete spectra. And that's what we're going to cover in 3.3.1. But before we go in depth, on a very basic level, discrete spectra basically means we can count from one individual eigenvalue to another. So let's say, for example, that q is equal to positive integers, n, where n is equal to 1, 2, 3, 4, etc., all the way to infinity. So we can count from one q to another. We can say, it starts at 1, it goes to 2, it goes to 3, it goes to 4, right? In contrast to that, the second type of possible value that q can take on is called a continuous spectra. Remember, spectra is basically just a fancy vocabulary word that represents the type of values that q can take. So in the terms of continuous spectra, this would be something like, for example, q equals x, where x is any real number. And this is different from a discrete spectra because a continuous spectra cannot be counted from one value to the next. Let's say I start with q equals 1. Okay, what comes after q equals 1? If x is any real number, do I say q after 1 is 1.1? 1.01, maybe 1.001. You see how it sort of goes on forever. There's not really the next eigenvalue that I can count to. It's uncountable because it's continuous. So it goes, on a continuous line. So because of that, it represents, instead of sort of discrete values, it takes on just an entire equation domain, sort of. So in general, if you have continuous spectrums, these result in physically unrealizable wave functions. So basically, if you were to get a continuous spectrum when you operate on an eigenfunction with a Hermitian operator, what that sort of implies is that your eigenfunction, and therefore your wave function, is not normalizable, which means that it is something that is not possible to represent in a physical sense. Remember, for example, free particles in our sort of stationary states system, right? In contrast, discrete spectra are physically realizable. So the reason why we're looking at discrete spectra first is because these sort of systems are actually ones that can happen in physical reality. Whereas in contrast, these are impossible, right? If you ever have a wave function that is defined in terms of a continuous spectra when plugging into the eigenvalue expression, either your operator is not Hermitian or your wave function is not a physically possible wave function. That being said, we still are going to look at these later down the line because they have very unique mathematical properties that make it so that if we can understand them, they sort of help us understand some other more complicated systems down the line, right? Think of the same reason why we even bother to study, free particles, because free particles technically are not physically realizable in the stationary states. So, because of that, we're going to start with discrete spectra and start right away with 3.3.1. So 3.3.1 is sort of going to set the foundation for everything that we look at later in chapter 3, because remember, ultimately chapter 3 is going to go through everything that you learn in chapter 2, but just through the window of linear algebra instead of, calculus and traditional algebra. So because of that, we have to start off by setting up a number of very basic theorems so that we can work off of those and sort of actually start being able to study more complicated systems. Think of this as an analogy to sort of when we started in chapter 2 and we defined what stationary states even were, all the theorems involving stationary states, completeness theorem, using Fourier's tricks, all that stuff. Basically, 3.3.1 is a very technical chapter, and it basically introduces us to a number of fundamental theorems that we will use to actually build off of to analyze more complicated systems. So because of that, this is a very rigorous sort of proof-based section where we're going to just basically introduce 3 statements, and we're going to prove those 3 statements. And we're going to say, okay, these are the 3 fundamental things that are sort of what we're going to use as a basis for all of our logic that follows afterwards. So let's start. So for discrete spectrums, I'm going to say discrete spectrums, and therefore realizable wave functions have 3 properties, or 3 fundamental properties. And as we go through these, you will very quickly see that they are actually quite similar to the fundamental properties of stationary states at the start of chapter 2. So let's start with theorem 1, which is going to say the eigenvalues of discrete spectra are real. So let's prove this. So I start off with my eigenfunction expression. Q hat operated on our eigenfunction f is going to give me the eigenvalue little q multiplied by that same eigenfunction f. So remember, we're dealing with real systems, and also given the fact that we're assuming that this is a system that is real, we can also assume that the operator that we're measuring is also going to be real. So therefore, we can safely assume that Q hat is going to be Hermitian. So I'm going to write out the definition of Hermiticity in terms of inner product notation. And from this point, I'm just going to take advantage of this definition and rewrite both of these in terms of little q. So f inner product with little q f is equivalent to the inner product of little q f with f. And then the next thing I can recognize is q is an eigenvalue. So because of the fact that it's an eigenvalue, it is a number. And because of the fact that it's a number, that means that we can bring it out of my integral. Because remember, this inner product notation is just an integral in disguise, right? So if I bring out the q from this integral, what I really have is, well, this q just comes out as normal. And I have an inner product of f with itself. And this is going to equal, well, here, remember, if it's at the start of the inner product, there's a complex conjugate applied to it. So if I bring it out, I'm going to bring the complex conjugate out with it, multiplied by the inner product of f with itself. Well, in this case, these two just cancel, which tells me that q has to equal q star. If q is just a number, the only way for this statement is to be true is for q to be real. Therefore, theorem 1 has been proven. The eigenvalues of discrete spectra are always going to be real. Now let's move on to Theorem 2. Okay, Theorem 2, which is going to sound very familiar, is going to tell us that eigenfunctions of distinct eigenvalues are orthogonal. This hopefully sounds very similar to the orthogonality statement for stationary state wave functions. Now, let's actually see what this means. So, let's suppose that I have two separate eigenvalue expressions with two different eigenfunctions for the same operator. So I'm going to say q hat operated on my eigenfunction f is going to give me, I'm sorry, I'm still sick, but it's going to give me little q, which is the eigenvalue for f, multiplied by f, and I'm going to operate on the same operator, but this time on a new eigenfunction g, and this is going to give me a separate eigenvalue, let's call it q prime, on not f, but g, just like this. So basically, I have the same Hermitian operator. I'm operating on two different eigenfunctions, and I am getting two separate eigenvalues, a q and a q prime. So, given that q is Hermitian, suppose that I set it up like this. Suppose that I set up an inner product of f with q hat acting on g. Assuming that q hat is Hermitian, this means that this is the same thing as the inner product of q hat acting on f, inner product with g. In which case, this means that if I then represent this in terms of the eigenvalue expression, q hat times g is going to give me q prime times g, which I can then bring out of my integral. So q prime times the inner product of f with g is equal, here, same thing, right? Q half times f is going to give me q times f. Since it's at the start of the inner product, I bring it out and it takes the complex conjugate with it, giving me q star times the inner product of f with g. In which case, at this point, this and this go away, right? So this and this are not generally equal because these are two different eigenfunctions, right? F and g are two separate eigenfunctions. That implies that their eigenvalues are going to be different as well. So q prime and q star don't necessarily equal each other. What that means is that the only way for this expression to be true is if this term, aka the inner product of f and g, is 0. And remember back in at the start of chapter 3, one of the things we defined about the inner product was that if two separate functions that are not the same have an inner product of 0, that implies that they are orthogonal with each other. And this is sort of a very elegant callback because it indirectly sort of proves why stationary states are orthogonal. Because remember, stationary states are eigenfunctions of the Hamiltonian, where the distinct eigenvalues are energy, right? If you measure the Hamiltonian on your stationary states, you get their energies. If you act on the stationary state eigenfunctions with the Hamiltonians, you get energy, right? H hat times psi is going to give you the energy of the system times psi, given that psi is some sort of stationary state. We have seen this over and over in chapter 2, and at the very start, we sort of made a slightly messy and not very intuitive proof that sort of explained why the individual stationary states were orthogonal to each other, right? Imagine, the infinite square well. We said that the stationary states of the infinite square well, or the stationary states of the harmonic oscillator, all of them are orthogonal with each other. And the explanation for it was kind of a half-ass, because Griffiths said so. Here we're seeing through the eyes of linear algebra why this is true. And the difference here is that this proof is actually a lot more general compared to the one we had in chapter 2, because the one we had in chapter 2 basically said that, okay, stationary states are orthogonal to each other. So in chapter 2, we had the idea that for any given system, in assuming that the system was a stationary state, then its individual wave functions for each energy level would be orthogonal with each other. Key point here being that the state has to be stationary. Here we have defined a much more general expression, which basically says that as long as, I have distinct eigenvalues, aka as long as my wave function is a physically possible wave function, then as long as I have distinct eigenvalues, then the wave functions are always going to be orthogonal. It doesn't matter if they're stationary or not. So automatically we've taken the sort of very shaky proof that we had at the start of chapter 2, proving orthogonality for stationary states, and we proved it in a much more solid way through linear algebra, and we also expanded it so that it's not just stationary states, but just all physically realizable wave functions that follow this property. And this is very useful because automatically this implies that we can go on and start utilizing things like Fourier's tricks and all that stuff. So all of the stuff that helped us solve systems in chapter 2, we can now apply to not stationary states. And because of that, now automatically, we can start analyzing much more complicated systems. Now, there is one problem here, and it's that this theorem does not account for degenerate states. Imagine, for example, if Q equals Q prime, in this case, this tells us nothing, right? If Q equals Q prime, then this statement is just true without the inner product of f and g having to equal 0. So because of that, if somehow your eigenvalues had degenerate states, as we saw in the problems for this earlier sections in chapter 3, in that case, this theorem doesn't tell us anything. It doesn't help us. However, it turns out, and this is something that you're going to have to take Griffiths' word for, it turns out that if you have eigenfunctions that share the same eigenvalue, it turns out that a linear combination of them, any linear combination of them, is itself also an eigenfunction with the same eigenvalue. So let's visualize this. So let's say that f and q are degenerate eigenfunctions. So let's say operating q hat on f gives me q times f, and let's say operating q on g also gives me q times g. Whoops, q times g. So these two eigenfunctions are degenerate. They give me the same eigenvalue when I operate q on them. So Griffiths is making the claim that if this is true, then in fact, if I operate q on any linear combination of f and g, so c1 times f plus c2 times g, this is also going to give me q times that same linear combination. And he makes this claim right now, and it turns out that later down the line in sort of problem 3.7, we're going to prove this, and it turns out that if this is true, it's actually possible to use something that's called the Gram-Schmidt orthogonalization procedure, and it basically lets you choose a separate set of eigenfunctions that are still valid for the given degenerate system, but are actually ending up as degenerate with each other. Or, sorry, it's possible to choose a separate set of eigenfunctions that still have the same degenerate eigenvalues, but they turn out to be orthogonal with each other. So let's assume that you had some, fantasy wave function, and you had two valid wave functions for it for two valid energy states, f and g, and these two were degenerate. In that case, basically, the Gram-Schmidt orthogonalization procedure is this mathematical formula you can use, which lets you choose two new wave functions. I'm going to call them f prime and g prime. And these two new wave functions actually turn out to represent the exact same system, with the only difference being that f prime and g prime are guaranteed to be orthogonal with each other. So f prime and g prime such that the inner product of f prime with g prime is going to be 0 no matter what. This is a very painful procedure. Given some of the problems that we have done in this chapter, the fact that Griffiths himself is actually saying that this is a very painful procedure should give you an idea of just how complicated and just painful doing this actually will be. If you want to do it, there is a problem at the end of the book in the appendix that sort of showcases this procedure. But thankfully, in general, we will have techniques that sort of allow us to bypass it once we actually do encounter these kinds of systems later down the line. But that's not important. Putting all that aside, the conclusion sort of for all of this is that in general, assuming you're dealing with a physically realizable state, its eigenfunctions, even ones with degeneracy, can always be set so that they are orthogonal to each other, and assuming that you've normalized everything, orthonormal to each other. And this is a very useful property because, once again, it allows us to use Fourier's trick, which becomes very useful because if we can use Fourier's trick, then we can use all the techniques we used in chapter 2. We can find the probability of being in each individual energy state, all that same stuff. So that's just a very nice thing. Next, we will move on to the third theorem and the final theorem for discrete systems. Okay, the final theorem is not something that we're actually going to prove because proving it is very complicated, and it's the same thing that we saw in chapter 2. So theorem 3 is basically, it's going to tell you that the eigenfunctions for an observable operator Q hat are complete. So if you remember the completeness theorem back in chapter 2, basically you can use the set of wave functions for a system and you can use them to create any other wave function through a linear combination of those wave functions, right? This still applies for chapter 3, right? These eigenfunctions, remember, are analogous to wave functions. So if wave functions have completeness, then eigenfunctions will also have completeness. Now, in chapter 2, we mentioned how proving completeness is a very complicated thing that is more rooted in something that a math major would want to do rather than a physics major. The same thing applies to completeness theorem for eigenfunctions. So because of that, we will not bother to prove it. It's just something that we're going to state. We're going to assume that eigenfunctions are complete, at least for physically realizable systems, in the case of discrete spectra anyway. And that gives us our 3 fundamental properties. We can then use these and build off of them and start analyzing all of the systems that are represented with discrete spectra. So now let's start doing the problems for 3.3.1, and then we will move on to continuous spectrum.